Let us look at Fermat's little theorem. Now, this theorem is specifically for multiplicative groups, not additive groups. In multiplicative group of non-zero residue classes, modulo P is G equal to 1, 2, 3, and so on up to P minus 1, because those are the only possible remainders under multiplication. If P is prime and A is an integer not divisible by P, this is what we mean by saying that there are no zero remainders. Then A to the power of P minus 1 is congruent to 1 mod P. So let's see how we arrive at that. Now here in this group of non-zero residue classes modulo P, the order is P minus 1. If A is co-prime to P, that is the GCD of A and P is equal to 1, then multiplication by A permutes the elements of G. Permutes basically means it rearranges the numbers. Let's multiply the elements by A. So what we get is A times 1, A times 2, A times 3, and so on up to A times P minus 1 is equivalent to or congruent to 1, 2, 3 dot 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 P minus 1 mod P. Let's multiply all these elements. So A times 1 times A times 2 times A times 3 and so on up to A times P minus 1 is equivalent to 1, 2, 3 and so on up to P minus 1 mod P. Now, how many A's are there? There are P minus 1 times A is there. So that means A to the power of P minus 1 times. Now, when we say 1, 2, 3 and so on up to P minus 1 being multiplied, it is equal to P minus 1 factorial is congruent to P minus 1 factorial mod P. We can cancel P minus 1 factorial on both sides since P minus 1 factorial is co-prime to P. Now, how can we say that P minus 1 factorial is co-prime to P? You know, P is prime. P minus 1 factorial is 1 times 2 times 3 times up to P minus 1. Every factor of this product is strictly less than P. So none of them is divisible by P. Therefore, the product itself, that is P minus 1 factorial, is not divisible by P. So P minus 1 factorial has a multiplicative inverse mod P, which allows cancellation. Okay, let's continue here. Since we are cancelling P minus 1 factorial on both sides, we are left with A to the power of P minus 1 is congruent to 1 mod P. So that is what we had to prove, or rather that is what the Fermat's little theorem is saying. So let's take an example and see what it means. Let us take P equal to 7 and A equal to 3. Now here 7 and 3 are co-prime. That means GCD of 7 and 3 is equal to 1. So let's apply this to this formula. A to the power of A is 3. P is 7. So A to the power of 7 minus 1 is equal to 3 to the power of 6, which is equal to 729. And if we divide it by 7, the remainder will be 1. So we can say 729 is congruent to 1 mod 7. Okay. Now, what happens if A and P are not co-primes? Means that P divides A, which implies since it divides A, that means A is congruent to 0 mod P. So A to the power of P minus 1 is congruent to 0 mod P if A and P are not co-primes. Now this Fermat's little theorem only talks of A and P being co-primes. This is just for additional information. Now here, Fermat's little theorem came before Lagrange's theorem, even though it seems to fall out of Lagrange's theorem. Group theory was not developed in the time of Fermat. Now, Fermat arrived at this theorem by reasoning with remainders, what we now call modular arithmetic. So what we have seen now is the group theoretic formulation of the same. So remember, Fermat's little theorem is not applicable to additive groups, because in additive groups, a to the power of something doesn't make sense. That is why it is applicable to only multiplicative groups. Okay, again, let me remind you, there is a link to a PDF book which describes all these in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now.